going infinitely far with this paraboloid? Does it just keep going? No, because I know something, right? Where am I cutting it off at for y? At y equals 4, right? So I'm going to do is I'm going to draw my paraboloid here, and I'm going to cut it at 4. Okay, so this is my solid, and that's honestly all we have to do, because the next thing we want to do is look at the cross section. Now we're going to play down with it. You probably have an idea of where you want your cross section, but I'm going to try some other things. First thing I'm going to try, can I take it with z? Well, I could, right? Let's talk about what will happen if I cut this with z. If I cut it with z, I'll be taking a slice right across here, right? Everyone's okay with that? If I take that slice, as I look at my paraboloid from on top, what is the shape going to be? Well, if I were to look at this shape, think about your paraboloid, if I were to look at it on top, looking down, what variable am I ignoring? Z. What would it look like? Parabola, right? So if I take it with z, I can just kind of ignore z to get a good idea. I know that it would look like a parabola, right? Which way would this parabola be facing? The y direction, positive or negative? Positive, right? I can tell that because y equals x squared is positive, right? And it would come off, right, at 4. Can I do that? Yeah, it's got a general shape, right? No matter if I cut it here, down here, it's always going to have the same general shape, right? So I can do that. Let's talk about another one. I can also cut it with x. If I cut it with x, that means I would take a certain x value, maybe out here somewhere, right? And I would cut it. I would cut it here, 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 going across like big slices of it. If I were to cut x, we can ignore x and look at what shape would we have. Parabola, right? So I cut x. When I draw this out, I'm going to write it as y and z. I want you to be very careful here. Which way is my parabola facing? Y, and it's opening positive, right? So y equals z squared. Should look like this. Well, could I do those types of cross sections? Totally, right? I can do those as well. Now, both of those are nice, but the really nice one is y. What shape do I get if I take this jump and I take cross sections along y? Circle, right? I can tell that because let's ignore y for a second. X squared plus z squared, that would definitely give me a circle of some radius, right? So what I'm going to do is I'm going to cut it that way. Like this. I'm going to take that cross section, I'm going to plunk it down here. It does not matter which of these three methods you use. All three of them can be done. We'll be able to solve the problem all three ways. But let's think back. What did we think about this thing right here? Polar. Which of these is going to be nice for polar coordinates? This jump right here, right? We choose the one we want. We choose the one that's nicest for us. Sometimes only one of them will work. Sometimes all three of them will work. If all three of them work, choose the one that is nicest. So if we've got that, we got our solid, help us get our cross section. The next thing we need to do is find some bounds. You guys told me I'm going to take my cross sections across to y, right? The first thing I have to do is find my bounds for y. Now we've got to think about this for a second here. When I take my cross sections for the second part, and before that, when I look at my bounds for y, what I'm talking about is where exactly am I integrating across? Well, this is going to be running from all the way out here, right? And am I always going to run it from 4 back? Is my solid always from 4 to 0? No, right? My solid doesn't always stretch all the way back. Rather, my solid stretches from 4, right? Ow, my markers are dead. From 4, and it goes back a certain distance, right? Until it hits the solid. That is the back wall of it. So what I have is a front wall of my solid and a back wall of my solid. These are going to form the bounds. Well, first of all, what is this outer bound here? 4, right? So I'm going to write 4. I know one of my bounds is 4. And when I think about this, this is going to go from 4 back to this right there. What creates this back wall of my shape? This is my paraboloid, right? Y equals x squared plus b squared. Which means my other bound is going to be y squared, sorry, not y squared, x squared plus z squared. Which of these is my upper bound? Which of them is my lower bound? Here's 4 is the upper bound. What do you think? How can you tell? Because I have a picture. That's exactly right. You got to have that picture, right? We're going to be working our drawing a lot here. What else can I tell?
Farthest distance.
It's the furthest away, right? It's the furthest away from my projection. I go furthest out on that one. So I know I'm going to bound y between 4 and x squared plus b squared. Okay, so what you're telling me is right now when I set up this integral, I can set it up as double integral over some d, whatever the heck that thing is right there. And the inside of it would run from x squared plus y squared to 4, right? What would be on the inside of this graph? X squared. Yeah. Why do I keep finding what y's in there? I don't know. It's a Monday. X squared plus y squared. What? Here in dy, looks good. And then I'm going to write it as question. Now, in reality, I'm going to have to worry about this, right? In reality, I'm going to have to change it around somehow. But for right now, this is just an integral. Right? This is just something we're dealing with. What I want is I want to give you a second. I want you to try and integrate that. Give me a second. I want you to try it. How's it going? For those of you who look positive about this, you shouldn't. You should look really, really sad. You're going to run into all kinds of problems, and that's because as it's a Monday, summer screwed up. I apologize. At least we hadn't done anything with it yet. There we go. Big question, though. What would have happened there? Let's say that had actually been the problem. Integrating that wouldn't have worked very well, right? We could have done a couple things. When we have a square root and we're trying to integrate and it's not going well, what's the method you learned in Calc 2 to deal with that? Trig substitution, which would have sucked, right? What can we have done instead of trig substitution? We could have come back, right? We said all 3 methods worked. If this one gives us a gross integral, what can we do? Choose a different one, right? So it's really important we understand there are multiple options with these. Luckily, though, I just wrote it wrong, which makes my life millions of times easier. Why is this millions of times easier? This is just a constant value, right? Which means in reality, when I integrate this, I'll go ahead and I'll write this as an integral over d. I'll add square root x squared plus z squared. Just keep wanting to write y for some reason. I'll have y, right? And it's very important that when you integrate it, you write in your bounds. y equals x squared plus z squared, y equals 4. Okay. So integrating only on the inside right now. We're going to know later on that this doesn't matter if you do it first or set it all the way out first. Okay, when I do this, what am I going to get? What do I plug in first? 4, right? So I'll get 4, so root x squared plus z squared, minus, right? X squared plus z squared square root x squared plus z squared. dA. What did we say? It looks really awful. What can I do to clean it up? What do you notice that both of those things have in common? Both terms have the square root of x squared plus z squared, right? So what I'm going to do is when I rewrite this over d, I'm going to go ahead and factor that out a little bit. I'm going to write it as, square root x squared plus z squared times, and if I factor out the x squared plus z squared under the square root, I'm going to be left with a 4, right? What? Right? Yeah. The reason why we did this right now, why we did the first one rather than set it all the way up, is because you guys told me that when I looked at this cross section, this looked like it should be polar, right? When I write things in polar coordinates, it doesn't have an x and a y. What does it have? R and a theta. How many dimensions are polar coordinates in? 2, right? Which meant I couldn't convert it to polar coordinates here because I actually had 3 variables, right? It would have caused a problem. That's why we integrated with respect to the first one. Now, we can totally set this up in polar coordinates, right? Let's think about how we're going to do it, though. What is x going to be equal to? R cosine theta? What would z be equal to then? R sine theta, right? If we're converting it to polar, we need to make sure we understand why. I see this square stuff, I'm thinking it's going to be polar. I see this circle thing, definitely polar. If I'm doing this with respect to polar coordinates, though, I need to find my bounds. Talk about theta. That circle goes all the way around. What's theta going to be in between? 0 to 2 pi. Now, my children, this is where things get interesting. Let's think about this. When I look at this, I take a cross section, right? What is the largest? The biggest one is going to be all the way out here, right? Which means the largest this is going to get is 4 equals x squared plus z squared, right? Well, good. Which means my radius, the biggest it's going to get is 2. What is the smallest this radius could be? 0. Exactly right. These are so fantastic. Okay. Looks good. Looks fantastic. Which means if I set this up, which one goes on the outside? Right there. What do you think? Sound good? 0 to 2 pi. 0 to 2. What is this junk right here going to be? X squared plus z squared. What's that the same as? R squared. It's R. This is awesome. I'm really excited this morning. Good now. Okay. Okay, that's R. Guide. Fantastic. I have 4. And maybe I shouldn't have distributed that negative in because it's only going to be 4 minus what? R squared. Don't forget another R. You already say that. Notice that another benefit of integrating the z first was as soon as I did that, this just became a double integral. It was a lot simpler than having to set all the different bounds.